All right, folks. Welcome back. Good to see you. We just have a little bit left on last lecture, Introduction to Animation. So I'll just finish that up now. So we left off starting at this point where I was going to tell you about rigging. And rigging is really a set of techniques and engineering tools that have been developed in character animation very pragmatically to enable folks to control characters more intuitively and with higher level function. So you can augment a character with controls to easily change its pose, create different facial expressions, bulge the muscles, etc. Almost control anything that you can creatively imagine would be of use to control, or that for a particular application or maybe sequence of shots in a movie would be useful to control. You can think of rigging as like the strings on a marionette. Marionette's like a puppet. So the puppet strings allow us to control the movements of the puppet from afar. And rigging is like software controls that allow us to do a similar thing for digital character animation. The rigging's job is to capture a space of meaningful deformations of the character. And it's going to vary, right, from character to character. It will for sure be application specific. It'll be character specific. And the skeleton that we looked at last time is one type of rigging, but there's many more types. To give you a sense of some of these, actually visually, I want to play this short clip for you. But before I play the clip, you can see this character. The character's name is Ariane. You can see a bunch of rigs that have been actually visualized on top of this rendering in order to give you a sense of the controls you have. So for example, one of the most obvious ones is you can see this set of this little sort of, I don't know, large pair of glasses here with two circles on it. This rig is something that can be positioned in 3D space so that, and its job is to direct the gaze of this character, of Ariane. So wherever these two circles are, the pupils of the character are going to point in exactly that direction. You'll see this in the animation when it plays. Another set of rigs are these blue dots above the eyebrows or in the middle of the eyebrows. These are actually like keyframe or what I'm trying to say, control points for the curve of the eyebrows. And there's other rigs that actually I'm not exactly sure how they work, but or exactly how they're parameterized, but you can get a sense of them all over the body. These like little circles that will allow you to control presumably different positions on them, even this flap of hair, exactly which way it's moving in the wind, each of the fingers, things like that. Okay. There's a lot of rigs in order to be able to control this character in full. Let me play the video for you. All right. Uh, I got a question. So is rigging like moving a character's bones and skinning like moving the character's skin, hair, and clothing, all of the accessories? And it's a good question. I don't think the definitional boundary between rigging and skinning is that clear. And you probably got a sense of that from this video, where the rigging for this Ariane character and a bunch of the associate accessories, like this motorcycle, for example, in this scene, presents a range of different useful controls of these characters and accessories in some very programmatically sophisticated ways that are obviously really useful. Let me give one example, which is the bike has some rigging, at least as they're describing here, so that the wheels won't penetrate the ground, and as the whatever surface it's on, the bike will sort of follow that. That's obviously something that can be programmed and has been done here, and is something that gives the ability to then move the position of the bike over the surface and have it sort of lay on top of the surface in an appropriate kind of way. And also much of the rigging here, for example, the eyebrows, the position of the face, we're not affecting the skeleton of or the bones of the Ariane character, or facial expressions or skinning or something that could be called skinning. So I think some of these terms that you've learned and that apply to different parts of these, you can get a sense, can be combined in different flexible ways. Okay, so that was just a little bit about rigging, give you a sense of this really common necessary technique that's used in developing characters and then building characters for character animation, digital character animation, and then building on top of those characters layers of control that can be intuitive rigging controls for animators and artists that use them. The last topic for this introduction to animation lecture is motion capture. So in motion capture, which we've already touched on or mentioned a few times in the lecture yesterday, or on Tuesday rather, the basic idea is that it's a data-driven approach to creating animation sequences by recording real-world performances, right? And the idea is to extract the pose for a digital character as a function of time from raw data and enable performances by actors, typically humans, in order to create that underlying animation data. One really, famous example is Andy Serkis, control the character of Gollum in The Two Towers. This picture, I think, tells you a lot on the right-hand side. So Andy Serkis is perched on top of a rock. He's wearing this, odd blue suit, and there's little balls on the suit that he's wearing at various different locations. And the technique of motion capture and the motion capture system that is tracking Andy Serkis in this performance are going to come up with the three-dimensional location of all the positions or the markers on the various parts of his body in order to create raw data from which to help drive the character posing of the Gollum character. You can see it can be not just for controlling the skeleton as the major little balls on the surface of the suit are going to be used for, but also on the face. So if you look closely, you can see on Andy Serkis's face, there's a bunch of little dots. They're actually like key frame, control points that have been painted onto his, literally onto his face, so that a tracking system, whether video or from multiple cameras, in order to create a 3D inference of the location of those dots in 3D space, can be used to map the location of his facial features onto a digital character. A little bit about motion capture. Optical is what I'm going to talk a little bit more about. It's a more common technique. Has been a more common technique for a while. In the past, there were other techniques that were employed, like magnetic systems for suits that were worn, or even mechanical systems. You kind of almost wear like a small robotic suit, where we talked about measuring the joint angles for a robot with a rigid skeleton. We talked about in forward kinematics and inverse kinematics. So you can almost think of it that way. A human character is going to wear some kind of robotic skeleton like that, and the joint angles or extensions for each of the arms is going to be on some kind of actuator system that can produce data. And so those could be ways as well in order to capture the raw data of motion. For optical motion capture, which has gone through lots of iterations, there's lots of custom built versions of these kinds of systems, but they tend to operate on pretty similar principles. One common system, for example, uses markers on the subject. You saw them in Andy Serkis. You saw them on Shaq in this previous picture here. Put markers on the subject, and then you image the scene from multiple camera locations at the same time around the character that is performing, and then infer what the 3D location of each of these markers is by triangulation from the multiple cameras. So this would be like a computer vision technique or a photogrammetry technique. Give you a sense of scale, typically something like more than 8 cameras operating at high speed, 240 frames per second is typical. And as you might imagine, things like occlusions are difficult problems to deal with because the body of the person, right, is inherently going to block visibility of the marker from multiple locations. So these kinds of practical difficulties or challenges in the data will need to be resolved. This is something that you can see here is a sense of like the kind of motion capture data. On the left-hand side is someone performing. In the middle is the series of dots representing the 3D or 3D locations have been inferred, and then it's been redrawn in 2D space, essentially just by rasterizing the spheres at the location of each of those dots. And on the right-hand side, you can see those dots being then remapped, applied to the skeleton of a digital character. Okay. And the motion data can be quite complex. As you can see, there are quite a few motion capture nodes there on those characters. So the dimensionality of this data set can be pretty high. So you can it can be a very data-rich kind of technique. So summary of some pros and cons of motion capture. Some strengths are it can capture large amounts of real data very quickly. The realism can be high. Also, you can put it onto, trained performers, world-class performers of the kinds, well, let me restate that, world-class executors of the kind of performance that's required. Why do we get actors to perform in, for movies? It's because they're trained in the kind of, emotional transference of the kind of characters' emotions through the expressions on their faces and their movements. And that's why even for digital characters, the ability to find a world-class performer and then map it onto the character is usually a really strong basis for providing an excellent digital character performance. Often there are teams of artists as well that will sort of clean up the details of that remapping from a human performance onto a digital character, so the details work for the specific sort of anatomical, specifics of the digital character. Some of motion capture's weaknesses include that it can be quite complex, can be a costly setup. Traditionally, it's done in a studio and requires, I give you a flavor for some of the things, it needs a large number of cameras, high speed, maybe infrared, things like that. Actually, that's really gone up and up and up. It's just, it can involve many, many high resolution cameras, depth cameras, maybe even 3D cameras, RGBD cameras, lots and lots of imaging technology. And as I mentioned already, the captured animation may not meet the artistic needs directly. It may require alterations. And that's very strong motivation for trying to perform motion capture without markers or just from, as we call it in computer vision, in the wild video. This is a special expertise of someone that I taught the course with last year, Professor Angju Kanazawa, who's one of the faculty in the computer vision group at Berkeley. And Professor Kanazawa was the person that has put together a lot of the technologies and brought them to a high level of performance in order to solve this very challenging problem, which is to take in the wild video, something you might download off YouTube, for example, and in concert, of course, with a lot of machine learning over data sets that have appropriate annotations from types of video like this through to 2D skeletons of human characters in them. Learn from that very large set of databases, and then be able to take wild type video and perform an estimate of the 3D location. You can see something that is pretty close to state of the art. It's a couple years old now, but it's a paper result from a paper by Professor Kanazawa that you can see on the right-hand side. So a couple people playing ping pong, and then deduction of what the pose is for those characters, and then redrawing them using those digital characters that you see there automatically. All right. That's the last slide for the lecture on introduction to animation. And the last slide is next time physical simulation, which is what we'll move to now. Okay. All right. This next topic is an introduction to physical simulation, which is a type of animation for computer graphics. But unlike character animation, we're not controlling a character per se, and we're not controlling it directly. Often we are controlling it indirectly by providing forces into a virtual world that will then have its own internal physics encoded digitally and that will propagate. So let's take a look at some, let's get into it and then look at some examples. So the basic, foundation for all of this stuff on physical simulation is movement of physical stuff. So it's going to come down to Newton's law. Okay, force equals mass times acceleration. So this simple equation is literally the thing that underlies everything we'll talk about today. And so as a simple example on the left-hand side, recall that if you throw a ball into the air, it follows a parabolic path. Gravity is, at least at the surface of Earth, essentially a constant, right, in the downward direction. And the position x of the particle that follows as it rises, given an initial velocity, as it rises and is accelerated down by gravity, it follows that parabolic curve with the equation as shown there. But it turns out, and so that's a very simple example of force equals mass times acceleration. The force in this case by gravity, and then the acceleration, the force given by gravitation, and then the acceleration as a result of that, translating into this, famous parabolic equation. So half times t squared times the acceleration squared plus t times the velocity plus x. This equation here, written in a form that we'll come back to over the course of today. Actually, maybe I'll take a moment to explain that a little bit more. So the x position, say at any moment in time here, x at a given time t plus the next increment. So we'll talk a lot about if I know the position of a particle, or more generally, if I know the state of the scene, in terms of all of the material in that scene at a point t, I'm interested in what it will become at point a little bit in the future, call it a delta plus delta t. This can be given in this case for the particle as the position at the beginning of this time interval. So the position x at t plus delta t times the velocity at that moment t plus half times this time interval delta t squared times the acceleration at that point t. Okay. So this can be described for a very simple particle, as shown on the left-hand side, but it will extend, it turns out, to lots of particles or even meshes of material that we can model, for example, as spring mass systems or mass spring systems, as we will. Once we've done this, we can obtain simulations like the one I showed you last time for cloth simulation. So in this case, this is a model of the cloth that is then being acted on by gravity, by friction with the underlying wooden body of the character, and with the air that's surrounding it. Here's another example, fluids. So in this case, the water here is modeled as a very large number, hundreds of thousands of particles, individual particle models that are that undergo force interactions with each other due to that model the incompressibility of water. There's force that's applied by some kind of tidal injection of some kind of tidal force, say from that right-hand side at that particular moment. And anyway, I'll talk more about this in a little bit. This turns out to be a pretty popular project for final projects in certain years. In general, particle systems are a good way to model a lot of this. As I've already alluded to, single particles are very simple to consider. I already described in the example of throwing a ball up and having it sort of propagate, at least only under gravity, that one can work out the acceleration and then the velocity change and then the position change through incremental updates, or one could imagine doing that. We're going to talk about that today. It turns out there's a lot of computational gotchas to doing that, and we'll talk about methods to make that actually converge in a reasonable way. Nevertheless, single particles are relatively simple to consider, and large groups of single particles can produce very interesting effects in modeling things like, it turns out, water or smoke, or even things, as we'll see, like cloth. And we can supplement the basic ballistic rules that I showed earlier for a particle under gravity with things like friction, drag, collisions, force fields, springs, interactions, other things like that. So we'll talk about that today. Let's look at a more specific example of things that we can model by mass and spring systems. So this is an example of modeling a dynamical system. Here's an example of a mass spring rope. So in this example, you can see there's a bunch of points, blue dots, right? Those are the particles in the system, and they're connected by little white line segments, which in the system, in this particle system, represent springs that are connecting each of those blue dots and that have a stretchiness according to Hooke's law that we'll get into later. The first dot here is a control point, and then gravity pulls the rest of the system down. Notice that as the anchor point the system is moved around, that movement is going to exert force on the rest of the system through the cascade of the springs here. Okay, somewhat similar to a rope. This particular rope has spring constants and then a very low resolution here, right? It's only about 10 segments of springs or so. So that has a certain kind of springiness, okay, to it that makes it feel like a pretty bouncy rope. But it turns out you can take this model and extend it in a pretty extreme way, and you can even simulate hair using it. This, of course, has thousands of those kinds of strands, and it's significantly harder at this simulation here because in this case, it's critical to model the fact that the hair strands can't pass through one another, for example. So that needs to be resolved in the simulation as it evolves. And the contact between the hairs will generate forces that prevent them from passing through each other, obviously, but also that generate frictional forces. But the idea is the same in principle as before, but scaled up and with the accurate modeling of these other forces that I mentioned. You can also do a 2D version of this mass spring system, right? So here you can see the array of particles. You can see the array of connections between them, line segments, representing the springs. And again, they're modeled with, very basic Hooke's law kind of a spring model. And there's gravity. But in addition, the user can exert forces on the system by pulling specific points on this mesh in different locations. And by doing that, we get a lot of emergent behavior from the emergent dynamic behavior in this system, because those forces then will transmit to other locations in the system through the connectivity here. This model is like something akin to a mesh, right, of springs, or maybe even something like a rudimentary piece of cloth. And to achieve the next rest state, those forces need to propagate through the system and then come to rest. So you can take that model that I showed before, that sort of cartoon model, and then extend it to something that models something like cloth. So here's an example, I'll show you a few, of pieces of cloth on the left-hand side that are photographed. The specific weaving of this cloth and the properties of the thread of this cloth have been measured and then encoded digitally into the simulation that you see on the right-hand side. And so what you'll see is that in these simulations, first the cloth is sort of imagined to be held up, but then sort of, at the start point, but then as the simulation is turned on, gravity pulls on it and then it relaxes. And the characteristics of the folds of these cloths are, as you can see from the simulation, subtly different from type of cloth to type of cloth. The exact number of folds, the quality of the folds is different, and the simulation is a validation of this kind of measurement and then modeling effort in order to match the cloth on the right-hand side. Oh, I got a couple questions. Could the earlier thing being sure about water, could that be used to model ocean waves? Yeah, it definitely can be. Another question, from my understanding, it's not a good method because the tip of the ocean wave sometimes self-intersect and is very sharp, which is not what we usually want from cloth simulation. Sure, it depends. It depends what kind of cloth, what kind of ocean wave so it would be. Like a tsunami versus a propagating wave. Okay. So let's get into some of the details of this. So a simple spring model is shown here. Really, it all comes from Hooke's law, which you may recall from a physics class. So in this idealized spring model, say we have two particles, often referred to in this lecture as particles A and B. So the force from A to B is equal to some constant, k sub s, spring constant times B minus A. And the boldface here for B and A referred to the vector locations, 3D vector locations of particles B and A. Okay, so B and A you can think of as 3D vectors. And the force that pulls B towards A is equal to the inverse of this. Okay, so negative of the force A to B. So very basic. The force pulls the 2 points together. The strength, in this case, as you can see, k sub s is proportional to the displacement. Okay, so the bigger the gap between these two springs, then the more they get pulled together. And k sub s is a spring coefficient. So that's basically the stiffness of this spring. So the higher k sub s, the stiffer it is, and the more it wants to quickly pull this spring together. One limitation of this really simple spring model is that this spring wants to have a zero length, as you can see here. So the force, right, is from A to B is k sub s times the gap. So if there's any gap between B minus A, this model would exert a force that wants to move them closer together. And the only time the force completely goes away is if they're at the same location, particles A and B, that is. Here's a model for a non-zero length spring. It's not that much more complicated conceptually, but the equation gets a little bit more involved. Let's take a look at it. So in this case, this is a spring with a non-zero rest length. The non-zero rest length, that just means that it wants to, if no forces are acting on it and it is not in motion, then the spring wants to have a certain length, and that length is given by this parameter little l here, okay, for length. So what happens here in this equation is just modified a little bit. In this case, we still have a spring constant. We still have, it's still proportional to a distance, but in this case, it's the distance difference, the length difference from the rest length L, right? So it's B minus A magnitude here is the length between B minus A, and as long as that doesn't equal to L, this term here will be a non-zero number. And then this thing over here, which we'll see again a few times in coming slides, is this is just, of course, a unit vector that points from A to B. So it's B minus A divided by the length of B minus A. Okay, so this thing here is this unit vector pointing from A to B. Okay, so this is a vector that points from A to B, that is proportional to the spring constant, and that is proportional to a deviation in length from the rest length, L. This model is, a little bit more realistic, a little bit easier to use in digital in simulation, but there's another problem. This model doesn't have any friction in it, right? Doesn't have any damping associated with it. So this oscillates forever as an ideal spring. So if you pull this spring a little bit from the rest length and let it go, it'll just continue, going back and forth periodically forever. Okay, let's keep going. And we'll start introducing damping. In order to introduce damping, we're going to talk about the derivatives. So I'll use V and A and X for a vector pointing to the location of an object or particle, V for a vector representing the vector velocity of that particle, and A for a vector acceleration. on that particle. But in some cases, we'll also use dot notation. This is useful in some cases. So x dot is just equal to the velocity. X double dot is equal to a. So one dot being each dot representing a derivative in time. Okay. Are vectors introduced to account for the fact that we may not stretch the spring in the same direction as it sits? Yeah, that's going to be one of the reasons. But in general, these particles that we're considering are going to exist in 3D space. And so the vectors here represent that, we want to just give a name for what its location is and not have to write little x, little y, little z all the time. So you can just think of it that way as a compact 3D notation. Just exactly how we use normal 3D notation, normal vector notation for 3D space. Someone asked, what does it mean to have a non-zero rest length? It just means that this is like an actual spring, okay, that you could go buy that has a certain length to it, and it's only gonna create a force that oscillates if you extend it or compress it first. So what is the rest length of that spring? Well, if you went and bought it and you just put it on the table, the rest length would be at rest. How long is it? Okay. Let's talk about motion damping. Okay, so these are all, pretty basic things. What have we done so far? We've talked about spring forces, and then we're going to talk about friction, basically. Okay, so these are all very basic things in a physics class. It turns out that all of these things are critical to model as well in a digital physical simulation system that's going to produce particle motion that has any chance of producing kind of realistic behaviors. Okay, so that's where we're going. Simple motion damping. So this is not going to be a useful model, but it'll be a starting point that we'll build on the next slide. So simple motion damping, let's say that we have a particle called B. Let's say it has a specific, some kind of velocity at this moment, B dot, okay? So a simple motion damping model is for the force to equal a force to be equal to negative k sub d times B dot. What does that mean? It's a k sub d is a constant. Okay, it's a damping constant. Negative because this force will point in the opposite direction from the velocity. And B dot is, of course, the velocity of this particle. Okay. You can think of this as behaving like viscous drag on the motion. So as you know, if something's moving through the air, like if you're driving on the freeway, the faster you drive, the larger the air resistance force on the car. This is akin to that kind of a force. Okay, it slows down motion in the direction of motion. So the force is going to point always in the opposite direction. In case of D is a damping coefficient. One problem with this simple motion damping is that, at least as relates to the spring motion that I talked about, is that this motion damping here will slow down all motion in the scene. So, for example, if we have a rusty spring that, we know that if you have some kind of spring, actually it doesn't need to be rusty. We know that in the real world, if you have any spring and you start it oscillating, it will slow down, okay? Even if it's a great spring, it's set up really well, there'll be losses in its energy as it goes through its oscillations, and eventually it will come to rest. So in this comment here, let's say we want a rusty spring's oscillation to slow down. Let's say we tried to introduce this kind of a damping term in order to cause that to happen. It will cause it to happen, but this term would also cause the two particles A and B on this spring to slow down as it falls towards the ground. Okay, maybe we want that, but it's unlikely that the rate at which the spring falls to Earth, which is probably related to, for example, the air resistance as it picks up, to high speed, that's going to be unrelated to the internal sort of damping of a spring. Okay, so in this line that development that we're talking about here mathematically, we're talking about internal damping for the spring. So this is a way to damp only the internal spring-driven motion, and have this be independent of any other motion. So, for example, this model that I'll go through here in a second is viscous drag only on change in the spring length itself, and it won't slow down the group motion of the spring system. For example, a global translation of the system or rotation of the group or something like that. Okay, so let's take a look at what's going on here. Here in this case, the damping force F sub A is equal to negative K sub D, similar to last time. And then we have these things here. So what's going on? First of all, again, we just have this term, which is a unit vector pointing from A to B. And then we have this term here. So let's take a look at it. This is equal to, again, this is a unit vector pointing from A to B. This thing here is the difference in the velocities of A and B, right? It's B dot minus A dot. So if you have these two particles in space, if one is moving in this direction, that would be its A dot vector. And if this particle here is moving in this direction, that would be its B dot vector. If you take those, the difference of those two in a vector sense, you end up with the net difference, vector difference in their velocities. And if you take a dot product of that with the unit vector pointing from A to B, this is a projection of the length of the difference in those vectors onto this unit vector pointing from first particle to the second particle. So the net of this is that this is a force that's going to only slow down or act in the opposite direction of motion of the spring, and will tend to slow down the motion of the spring by pointing in the opposite direction of the internal motion of the spring. But if the spring is rotating, for example, in space, this force is not going to slow it down. So this is specific to internal damping. I'm talking a lot about springs because it turns out that there'll be spring constants for mass spring systems are really useful for modeling physical simulation systems. And you're going to model a mass spring system in your last programming assignment to model a piece of cloth. Hopefully it'll be a really fun assignment. And so let me go through a few more details about this that are really critical in doing this kind of software engineering. In terms of spring constants, one thing that will come up if you try to engineer these kind of systems is what's the resolution of the mass spring system? For example, I showed earlier, a simple model with only 10 segments in the spring. It was a rope, right? And I observed that it was a pretty low resolution rope. What if you wanted to increase the resolution of that rope to like 20 segments or 100 segments? If you try to model that with, as we've done with the equations so far, using a constant k sub s in the equations like from Hooke's law, it turns out that if you increase the discretization, you won't get the same behavior for that between those two springs. That's shown here. So if you have one spring of length L, and if we want to double the resolution, let's say one segment of a mass spring system with rest length L, if we consider doubling the resolution, what that says is that we'll have two segments of spring elements here, each of length L over 2. And if there was an extension in this spring of delta L originally, that's going to be equivalent to having each of these two subsprings elements here extended by half the distance, right? Delta L over 2. It turns out that this is not going to have the same force, total force on this, if you have the same k sub s for these two spring constants. And so, let me see. It's sort of trivial algebraically to write it out. Not a bad exercise to do it, to check and see how exactly that occurs. But it turns out these are not mathematically equivalent at all. And if you, of course, want to freely change the resolution of your system to be able to, say, debug at low resolution and then scale it up to high resolution for rendering out a final simulation run, this will have completely different dynamics and it will look completely different when it's at high resolution. Not exactly what you want. So the problem here is that this constant k sub s for the spring constant gives inconsistent results that are dependent on the discretization level of the spring mass structures. And the solution is to work with not a change in the length, in the absolute length of the springs, but rather to consider the strain, which is a relative change in the length. So it's going to be the change in length as a fraction of the original length here, as shown here. So the change delta L relative to the original length or rest length, if you will, L sub 0. So that turns out to be the thing that mathematically will make it work out. There's a couple of ways to implement that. One is that you could divide the spring force by the spring length as a normalization. Second implementation is that you could normalize k sub s by the spring length as well. Okay. All right. Next, let's look at some topological issues in spring mass systems. What are the topologies? You can have ropes, as I mentioned, just a linear line. You can have sheets, as you can see here. You could have blocks, representing volumes, others, okay? Is a little bit up to your creativity for different applications. Let's take a look at some sheets and observe some of the connectivity requirements for achieving certain kinds of emergent properties of the dynamics of the sheet. So the behavior of the sheet and the dynamical behavior is going to be determined by the structural linkages. So here, for example, looks like a very reasonable structural connectivity, right? On the left-hand side, kind of a grid connectivity. But this turns out doesn't work well at all for physical simulation of something like cloth. The problem is that this structure will not resist shearing in any way. So I'm not sure if you can picture this, but if you pull along the two diagonal lines that are shown there, there's a way for this sheet to deform by all the squares becoming more like becoming diamonds or extreme diamonds and then shrinking to a line without exerting forces on the rest of the system. So this structure doesn't resist shearing anyway. It also turns out it doesn't resist bending out of the plane of this sheet, okay? Because the springs only exert force along the line or the vector direction connecting individual particles in the mass spring system. Here's a second try. We could enhance it by adding additional lines here as shown in teal, okay? So this structure will resist shearing to a degree. Why? Because if you try to pull on the diagonal now, in order for it to shear in the direction that I described earlier, like it would cause these 2 points to have to get closer together and it would compress that spring. Okay, so there'd be a spring normalizing force trying to avoid that. But it turns out this has an anisotropic bias. You could sort of try to reason it out, exactly what might happen if you try to push and pull on this sheet structure in a particular way, but you can tell that it's anisotropic in the sense that there's lines that only go teal in one direction, not in the other direction. You could try to reason about exactly what forces or dynamical transformations this one would allow that the next one doesn't. This one has less directional bias by sort of increasing the symmetry and putting these 2 crosses here, which does resist shearing a lot better. This structure, however, will not resist out of plane bending either. So you can sort of fold this piece of cloth up with no, resistive force at all. This structure here is a way to add additional springs to provide that out of plane bending. So here you can see these red connectivity, these red springs added from a skip level. Okay, so from each particle in this mass spring system to not its immediate neighbor, but 2 neighbors away. And it turns out that these red springs should be much weaker than all the other internal connectivity in order to just give enough resistance to out of plane bending for things to work in a reasonable way. If you do that kind of modeling, you can end up with a mass spring piece of cloth that could be modeled into like a dress, put onto a character, and it can that mass spring dress is just responding to the motion of that character and then to gravity in order to provide its dynamical behavior. All right, so that was a bit of a deep dive into mass spring systems and how you can build up from them into things like ropes and cloth. Will be very useful to you in that next assignment. Let's broaden this up a little bit and talk about some of the issues in being able to simulate exactly how this works. So when we do particle simulation, that is, we want to figure out with the modeling of all those forces in some kind of system, and then we want to say, okay, let's start now. I want to know how this system is going to dynamically evolve over time. So how do we do that? I alluded to it at the beginning. Okay, we can sort of say, okay, let's take small time steps, and within those time steps, say what the apply Newton's law, F equals ma, and figure what the total forces on the system are, translate them into accelerations for each of those particles, and then evolve those to update the velocities and evolve those to update the particles, okay? If you do that in the simplest possible way, that's something called Euler's method, okay? So Euler's method is extremely famous because if you try to apply this notion of F equals ma in the very, very simplest kind of a way, you'll end up with some kind of structure like this. It also turns out that Euler's method is very inaccurate and is extremely unstable, which is actually the larger problem. And we're going to get into those issues today because those are at the foundation of doing physical simulation, or actually any kind of numerical propagation of ordinary differential equations, which is what we'll be doing here. Okay, so Euler's method. So what is it? By the way, also Euler's method, this is a very old field. It has a lot of history in it. So there's a lot of different names for these methods. It's called Euler's method. It's also sometimes called forward Euler. It's also sometimes called the explicit method, or explicit forward method. Okay, so what is it? It's an iterative method. We go from time step to time step. And oh yeah, thanks. The question and answer was given. What does unstable refer to? It diverges over time. That's exactly right. It'll blow up. Okay, we'll look at that in detail in a few slides. So, but what is it to start? It's an iterative method. So we start at one time step, and then we consider going to the next time step, and again and again and again to evolve over time. So what we do here is we say that the current the position for the next time step, so x at position t plus delta time rather t plus delta t, is equal to the position at the beginning of the interval x of t rather, plus delta t times the velocity at that at the beginning of the interval again x dot at t. Okay, then we update the velocity as well, so we say x dot at t plus delta t is equal to x dot of t, the original velocity, plus delta t times the acceleration at the beginning of the interval. Now, the key about this is that we use both the velocity at the beginning of the interval and the acceleration at the beginning of the interval in order to do the updates. This is really convenient because if you say right now, if I know that the position, the velocity, and the acceleration, that's all I need in order to apply Euler. Okay, I have everything that I need. And so I just update the position, update the velocity, I can go to the next time step. This is why it's really commonly used. It's very easy to do so. But as I mentioned, it has these really fundamental problems. So let's start to get into those problems. The first is error. With any numerical integration, particularly iterative ones of this kind, right, errors are going to accumulate. Euler integration is particularly bad. Let's take a look at an example over here. So let me see. Here it is. So here's the solution path in gray pink over here. Okay. And this here is an Euler estimate, or a series of Euler steps giving an overall Euler estimate of the path with small time steps. And here's one with large time steps over here, which is obviously much further from the correct answer. And it's easy to see why that happens. They all start at the same location. We take the position, the velocity, and the acceleration at that time. And then we update the location and the velocity by incrementing, by multiplying by the length of the time interval. So if we have a large time interval, then the update in the position is going to move further, linearly further, right, compared to the small time step. The problem then is that we get to a point in the space. You can think about this location in space here. It's a dynamic world. So at this location over here, the forces applying on a particle or anything in that region of the world are going to be different, of course, than the forces applying along the solution path. So then at this time step, when we attempt to apply the acceleration to the velocity, that velocity is going to be much further from the correct answer, and that will trickle down to our estimate of the x location over time. Okay, so you can see mechanistically how these errors are going to accumulate naturally. Wouldn't smaller time steps also mean that we have more numerical instability when calculating the velocity, since we're now dividing by a smaller number? This question is about whether would we have more numerical instability. No, this is not numerical instability in like a floating point sense. So hold that thought. This is going to be instability in a forward simulation sense, and it's a property, really, a mathematical property of not of floating point and sort of imprecision in a numerical sense at a like sort of a bit depth sense. This is actually something more fundamental. Hold that thought. Some pictures will really help. Okay, so errors and instability. So solving by numerical integration with finite differences leads to two problems, as I mentioned. The errors that at each step will accumulate. So accuracy decreases as the simulation proceeds always. However, errors are not, because as we'll see, if the instability is going to really be the thing, the blowing up part is the part that's going to be really problematic. Accuracy is just pretty important to mention for graphics applications. Accuracy may not be critical in graphics applications. As an example, like if you start like a wave, for example, you have like some water and you throw it into a box in your digital simulation, if it sort of splashes around the box and then comes to rest, eventually as like flat water, that might be fine, right? As long as it looks like water. Exactly whether it splashes really high or really low, or 4 times sloshing back and forth before it comes to rest, or 50 times in those details may be less important for a graphics application. But if you throw it into the box and the water just explodes and all the particles go to infinity, then of course that would be a more serious problem. Okay, so that's what instability is. In instability, the errors not just add up, they compound and they cause the simulation to diverge to infinity, even when the underlying force system does not have those properties at all. We'll look at a couple of examples. Okay, lack of stability is a fundamental problem in simulation, and it cannot be ignored. Let's look at a couple of examples of this. So, instability of the forward Euler method. These are two examples where as we propagate the solution, the particle goes to infinity increasingly rapidly, so it diverges exponentially, even though the underlying force field doesn't have any of those properties. Let's take a look at the top example first. So this is a world, okay, where the forces just go around in concentric circles from this center point here. So the little circles that are drawn here represent the directions of force, okay? And then there's two trajectories of particles that are drawn on here. It actually doesn't matter which one we look at. There's one that's sort of drawn here that you might see. It's a little bit harder to see. And there's a darker one here. They're just different time steps. It turns out it doesn't matter what time step you choose here. They'll both go to infinity exponentially. Let's just look at the darker one. It's a bit easier to see. So what happens here? What should happen here? If you drop a particle into this force field in the real world, what's going to happen? The particle is going to be there, and then it's going to start to accelerate in the direction of one of these circles, and then it's going to go round and round in a circle. Okay, so that's the nature of this, of this situation here. There's no chance that this, builds up speed and then flies off to infinity, nothing like that. This is kind of like a vortex, okay? But what happens if we try to simulate this system using forward Euler? So it's shown right here. Let's say we drop the particle in right at this location. It accumulates some velocity, okay, from that acceleration. So at the next time step, we find that velocity times delta t, increment to the x position is going to put the position over here now. And it's at a larger radius. That's the problem. Now, the force is proportional to the circle. The force is pointing it now in this direction. So the update in velocity plus delta t now puts the position of the particle over here. As you can see, it just goes out and out and out in this. It increases in diameter from the center point of this system, and off it goes in a spiral out to infinity. Let's take a look example at the bottom here. Okay, this is a different force field here, or a different world in which what's supposed to happen. Okay, it's something that's funneling all material into the flow along the x-axis. It's kind of like a drain. Okay, so anywhere you drop a particle into this system, it's going to bend it. It's going to move it towards the x-axis and then move it along a curved line so that it follows along these contour lines, and then it ends up moving along the x-axis, going to the right. But what happens if you simulate this forward Euler? It doesn't work because, for example, if you drop the particle in here, it's got a certain velocity that it picks up times delta t. If it pushes it over to the other side of this line here, it ends up higher up on the curve of these lines that are falling in, which means that it's going to accelerate further and push it even further out onto the next iteration, and so on and so forth. So this system is also going to explode, and it's going to go to infinity and blow up. So particles that are dropped into the system don't converge to the x-axis. Obviously, in computation, they go to the max value of your floating point very rapidly. Does the divergence here means the simulation diverges from GT? So I'm not sure what's meant by GT there. Maybe you could clarify. Okay, let me keep going. From ground truth. No, it means that it diverges literally to infinity. So, if you run this simulation and you have a variable XYZ for the location of your particle, one of those or all of those variables, depending on exactly the orientation, is going to go to max float, as the simulation propagates very quickly. That's what's meant by numerical instability in this case. It's a much more serious problem than getting away from the ground truth. It's that it literally blows up exponentially, and the values that you obtain are total garbage. It turns out that this instability is not just for the examples that I showed there, which maybe maybe that was helpful, maybe it seemed a little contract. It turns out it applies to the spring model that we looked at too. It takes a bit of reasoning to follow this, so let's try to walk it through and see exactly what's going to happen. Okay, let's go back to this model here and have this actually the simplest spring that we looked at, case of S times B minus A. That's all we'll need. So it turns out we'll be able to see that with forward Euler, if you distend this spring and start it a little bit away from zero length, it's going to start increasing its oscillation amplitude larger and larger with forward Euler until very rapidly the particle is whipping back and forth at max float velocity, and you get total garbage. Okay, unlike the behavior of the simple spring that, as we know, as we talked about earlier, if you separate a little bit in the real world, mathematically, it's just going to oscillate back and forth. From zero, it's just going to oscillate back and forth in the zero origin point, right? That's what it should do. So why does this happen? Let's just reason it through. So when the mass is moving inward, so let's say it's extended some distance, but it's in the portion of its period where the two particles are moving towards each other. What's happening? Mathematically, the force is decreasing, right? The separation is decreasing, therefore the velocity is proportional to the separation, so the velocity is decreasing, so the force is decreasing. That's the model here. But at each time step, we're going to overestimate the velocity change, because in forward Euler, we're going to take the velocity times the delta t and add it to the position. Okay, so even though the velocity is decreasing at that one time step, we're going to estimate the motion change in that particle to a displacement that's larger, because we've overestimated this decreasing velocity. When the mass gets to the origin, at this point, right, in the cycle, it's going to have a velocity then that is too high. Okay, it's now going to be starting to travel outwards. Let's reason. Maybe it'll get fixed up on the other side. So now the mass is moving outward. Okay, so what's happening here? The force is increasing, right? Because the displacement is increasing. Therefore, the force here, k sub s times b minus a, by this model is also supposed to be increasing. But at each time step, we're going to underestimate the velocity change. Okay. Okay. One second. Let me try. I say this exactly right. Yeah. Okay. So the mass is moving outward. At each of the time steps, as we're moving outward, we underestimate the velocity change because the force is increasing, and we. Oh, right. Change, which increases energy. Sorry, my brain is not working well today. Okay, yeah. Okay. When you're going in this direction, you overestimate the position because you underestimate the amount of force that's acting as you stretch out, because the more you stretch out, there's more force. So that means that you're going to go on, even on the outward direction, you're going to go further than you're supposed to, given the velocity at the origin. Okay, so it gets to the origin, it already has a velocity that's too high. And as it goes out, it's going to continue. It didn't get fixed up, unfortunately, on the outward bound journey. It's going to exacerbate the problem, and it's going to go further than it's supposed to, given that original velocity. relative to the mathematics, right? Okay, so now it's going to turn around, it's going to come back, and then we're back at the beginning of this. It's moving inward, force is decreasing, but it's going to get to the origin and it's going to be going even faster, okay? So this is a way of reasoning that as it goes inward, it's going to be speeding up. As it goes outward, it's going to be speeding up, and it just keeps whipping back and forth, and it will compound and blow up to infinity. So this is what I mean by instability being a foundational problem that has to be considered in this kind of forward simulation. Okay, so let's talk about it, combating instability. So some methods to combat instability are as follows. You can do a modified Euler. You could average the velocities at the start and end point before estimating before applying them to update the position of the particle and its velocity. This is pretty easy to do. I'll talk more about it later. It turns out it doesn't solve the fundamental problem of instability, but it could slow it down a little bit. A second method is you could try to adapt your step size. So for example, you could compare one step in time versus two half steps recursively, and keep doing that, recursing until you find an error between those two methods that is acceptable. That's a really nice method and recommended, although it can potentially require a lot of recursive sort of decrease in the step size. So it can be a bit difficult to apply in a practical way. There are implicit methods. These are advanced mathematical and computational methods that aim and actually are a fundamental solution to the instability problem. You can create so-called implicit methods that are always stable, that will never blow up. The key idea is to use the velocity to update the position, use the velocity at the next time step, not the current time step. It may sound like a small change, but it's recursive. In order to figure out the velocity at the next time step, you kind of need to know where the particle is going to be. Okay, so it's actually pretty difficult to do. I'll sketch that just so that you're aware of it, but it's beyond the scope of this class, but I think it's an important method to know about. The last and one that actually you're going to use in your assignment is called position-based or Verlet integration. This is a simple to apply method that constrains the positions and velocities of particles after each time step. It's very practical because by constraining the positions and velocities, we're going to just completely eliminate the possibility of it blowing up. And this can be done in a way that still produces or maintains a lot of the dynamical behaviors of systems for graphics. It's not accurate, but it produces the dynamical behaviors that for graphics may well be enough. Okay, so what's modified Euler? As I mentioned, average velocity at the start and the end of the step. This is okay if the system is not very stiff. Stiff, remember, refers to the spring constants in the system. But it turns out it's still unstable. You can't get away from it because of the contribution of using the velocity and the acceleration at the start. The update rules are written down here. Okay, so but the idea is just average velocity at start and end. This is the adaptive step size that I mentioned before. Pretty easy to describe, pretty easy to apply too. So it's a technique for choosing the step size dynamically or adaptively. And it's a highly recommended technique. So for example, you can run a change that is one x sub t change here. So one big T change in the step, and then or two x over t2 steps. And you can see that between those two applications, you do both of those for the current time step, right? Obviously. You can see that there's a deviation between the estimates of these two. So if it's not large enough, you could reduce the size of t and try again. And you can use applying two time steps in order to get a sort of a sanity check on whether the error is accumulating at too fast a rate or not. And anyway, so that's what that said there too. So the idea is that you might apply more steps in regions where there's higher curvature due to the forces in the system. The implicit Euler method is informally called backward methods. Forward Euler, or Euler being called forward method, implicit methods being called backward methods. The idea is to use derivatives in future points of the simulation rather than the current point in the simulation for the current update. And so simple to write down, here we use the velocity at time t plus delta t in this update. not at just velocity at time t as we wrote in the past. But easier said than done. In general, of course, you don't know what the velocity is going to be at this future time step. In general, there may be a function v or a function a for velocity and acceleration that, as a function of this, that attempts to estimate this velocity as a function of the position, the velocity, and the time at that location, the time at that moment. And if you set this up, then you can write this down as the next position or the next velocity estimate can be an update involving these abstracted functions here, v and a. And this turns into a multi-dimensional version of Newton's method to try to estimate what those target velocities at the end of and accelerations at the end of the interval are. This is solving a nonlinear problem for the position and the velocities at the end of the interval. It involves root finding, for example, like Newton's method. This kind of a method is slow. It can be difficult to implement, but it can be made unconditionally stable, which is a really useful property for simulations of this kind to have. More practically, for applications that don't require complete guarantees of that kind of a thing and can be implemented for, in class, in introductory class in computer graphics, is position-based or Vallée integration. So again, this is something that you'll do in your project. So the idea is you apply modified Euler to reduce the propensity for, or the rate of blowing up to begin with. But immediately after applying that forward step, will constrain the positions of the particles to prevent this divergent unstable behavior. And we'll use the constrained positions in order to calculate the velocity as well, thereby constraining the instability and velocity estimates as well. Both of these ideas are going to dissipate energy. Okay, they're going to throw away energy, which is inaccurate, but they will stabilize this simulation. So the pros and cons, it's fast, it's simple, relatively simple to implement. There's some specific details that, of course, need to be worked through in the software engineering. But it's not physically based at all, dissipates energy, which is a form of error. But it's highly recommended. And as I mentioned, that's what's going to be in the assignment. So here's some pseudocode for it. I'll just quickly walk through it. You get a chance to walk through it in detail as you implement it yourselves. First, we initialize all the particles, the vertices, vertices as they're called in this piece of pseudocode here. This is from Bender, Miller, and Macklin from a paper by those people. So you initialize the positions x sub I and velocities v sub I, and also the masses m sub I that are applied to some weights here, w sub I for force equals ma. For each of the particles from I equals 1 up to n. Okay, so you have n particles in this system. Then we loop, and for all the particles, we do an update of the velocity using f equals ma here. That's what this update term here represents. F external equals the sum of all the forces externally applying to this position. Then we update the positions p sub I, or create updated positions p sub I for all the x sub i's plus this is a forward Euler step here, as you can recognize. And then this is the constraint. So for all the particles I, we do a constraint application that constrains x sub I into the positions p sub I and applies a solver applies a constraint projection. It turns out you need to do this iteratively. In order to, if the particle is sort of stretched too far, you may need to sort of iteratively update it to recompact all the particles back into the constraint space. And this actually can't be bounded by a finite number of terms. So typically these things are swept under the rug, and you choose a maximum bound of applying these and fearlessly go forward. And this tends to work pretty well. And so you apply these constraints and a loop. And then after that, this is the final set of velocities, positions, and updating of all the velocities. Okay, so this is some brief pseudocode of applying or implementing physically based simulation of a particle system by applying modified Euler, and then basically applying constraints on the positions and velocities. Okay. Particle systems. So I mentioned this earlier already. Let's go into a bit more detail about particle systems. Particle systems are really fun and very powerful for modeling lots of different dynamical behavior. As I want to give you sort of a bird's eye view into many different things that can be and have been modeled. So we model dynamical systems as collections of large numbers of particles. Each particle's motion is defined by a set of physical, or it turns out, as you'll see some examples, non-physical forces. This is a really popular technique in graphics, in lots of games. It's easy to understand, easy to implement. It's very scalable because you can use a few particles if you want to go fast. You can bump it up if you want to go for higher complexity. The challenges are you may need many particles. For example, for fluids, I showed some examples earlier from sloshing water. I mentioned that there were hundreds of thousands of particles in there. That adds up a lot in computational cost. And you may need sophisticated software data structures similar to the acceleration structures we look at in geometry processing, like KD trees, or other hierarchical structures of that kind, in order to perform basic tasks, like, for example, finding the nearest particles for relative force interactions or things like that. So in a particle system animation, for each frame in the animation, if we need to, we create new particles, we calculate the forces on each particle, we update each particle's position and velocity, and then if needed, we remove dead particles from the system too, and then we render them. Okay, so that's kind of the general system model. What kinds of things might it be useful to put in? We've already looked at it, talked about a few. Attractive and repulsive forces, we talked about gravity, we talked about springs. There can also be forces like electromagnetism, propulsion. There are damping forces. We talked about sort of internal damping of springs, but very common. There's friction, air drag, viscosity as it plays a big role in fluid simulation of water simulation, for example. There are collisions. So particles may, interact or bounce off, have to bounce off in the walls of an environment. They may sit inside a container. They may be fixed objects inside the scene that they can't interpenetrate, or that they may exert forces onto, and vice versa. They may be dynamic objects in the scene, character body parts, so on and so forth. Okay, so collision forces can get pretty complicated and involve pretty complex force calculations. We already discussed springs, so this is an example of an internally damped non-zero length spring that we derived earlier in lecture. Simple gravity, right? Simple to understand. Close to the surface of the Earth, we have F equals negative mg, right? Always pointing downward. In general, of course, that's only at the surface of the Earth. So for things where we want to do a simulation in space, astro simulations, for example, then the general, the formula for general gravitational force between particles or between masses is going to be needed, as we see here. So gravitational force equals universal gravitational constant g times mass 1 times mass 2 divided by the distance between them squared. And this kind of a thing, of course, is used to simulate things like galaxies. This is a disk galaxy simulation from NASA. And so this is a particle simulation, large number of particles in here. And in this case, gravity being one of the primary forces acting in here, other astrophysics forces, solar forces, I'm sure, acting in here as well at the more local level. Okay, let's keep going. Particle-based fluids, I described this before. Here's an example of those particles in that water simulation. There's a force being applied at the left wall, as you can see, as it moves in. So the particles can't pass through the wall. So as the wall is displaced inward, it's exerting a force onto these particles, creating a wave, right? A compressive force, sort of piling up the particles. And then because they want to find a level, and then because of the internal viscosity of water, that will play out as a wave that propagates to the right-hand side and sloshing until rest is achieved. Things like granular materials have also become popular more recently in graphics. This is an example that shows a bunch of I guess, like coarse sand-like particles with a shovel going through it. Some things you may notice is that the other objects move with the shovel. Okay, so the simulation includes those kind of forces between the shovel and those objects. The objects also will push on the various granules in this space, and you'll notice that gravity sort of pulls some of the granules into the area after the shovel has passed, but it's not quite as liquid as water, right? It doesn't come to a perfect level. Here's another example, flocking birds. Flocking birds. This is a really interesting example. Let me start this video. This is not a simulation. I'll show that on the next slide. But this is live footage. And you can see all these different really rich dynamical properties of this really large particle, this really large flock of birds as it evolves as a unit. Right? We've often observed, it's sort of basic to large flocks of birds that they behave as like almost like an animal of its own that has a really a special set of emergent dynamical properties. You can see how little density portions sort of emerge in it of high density, and how those will sort of propagate out to sort of flesh out, which is natural because the birds that come bunched up too much don't want to be too bunched up, so they're flying into each other, so they'll try to space themselves out. The flock tends to want to go in a common direction, right, as you can see, but different portions of it may end up going in different directions, and it may sort of split and recombine and things like that. It turns out that's really well modeled as a flocking behavior as an ordinary differential equation, just a set of forces applying to a set of particles, as we've been talking about here. So you can model each bird as a particle subject to some very simple forces, attraction to the center of the neighbors. Okay, this sort of represents the behavior of birds, that they want to be in the flock, say for safety against predators, not wanting to be on the outside. Repulsion from individual neighbors. Of course, you don't want to fly into your neighbor and get injured. And then alignment towards the average trajectory of neighbors. So if everyone's flying in one direction, that's sort of a simple quote unquote force, is really a behavioral force, right? That sort of tends to orient that bird particles, so to speak, towards its neighbors. And if you do that, then you end up with a simulation that looks similar to what looks like the one in the top right there, as you can see. So it's very simple in order to model different kinds of behavioral characteristics. You can simulate this evolution of large particle systems numerically very interactively, very easily. You get emergent complex behavior. You can model lots of different kinds of animals, and people have fish, bees, different kinds of groupings of wildlife. You can run simulations for crowd simulations. You have some kind of architectural setup with exits, egress of people, so a flow of people into this crowded location, and then model how they can find the exits or not. This could be a model, for example, in a disaster situation where it's gone dark, or whatever other kinds of assumptions want to be made. And then this is the last slide for today. It's a bit more going on in here than just simple flocking behavior, particle flocking behavior, but I think it makes a few interesting points. That you can make really fun computer graphics with these kinds of building blocks of character animation. Simple this metal bar rotating here. And then many of these, the behavior of which direction these people are going can be modeled, could be modeled by that, the simple rules akin to that flocking behavior that I described earlier. But then many of the things in here obviously are pretty complicated and that we didn't touch on today, such as how do you calculate collisions between these complex non-particle objects, right? These are not just individual dots hitting a bar. In this case, there are, multi-segment skeleton characters with complex sort of surfaces that are colliding in a realistic looking way with other characters and not just sort of passing through each other and with the bar itself. And those, maybe that's a good way to sort of segue into number one. I'll leave it in the slides. There's more suggested reading if you find this topic interesting or are interested in doing a final project in the area of physical simulation. But maybe that last animation that I showed there is a good way to finish with this thought that we're just scratching the surface. Physical simulation is a huge field in graphics. Today we looked at an intro to particle systems, solving ODEs, but partial differential equations are what are needed for example, the diffusion equation, heat equation, Those are what are needed for simulating liquid, smoke, fire, as you saw examples of final projects that I showed yesterday. There are also rigid body simulations, which present other technical challenges. In fact, simulation of sound is something that, from the vibration of objects through to acoustic waves is something that is also an active branch of computer graphics. We looked at this mass spring dress system. That's what we studied today. This final picture I'll share here is, there are other ways to do these simulations. In fact, this is I think a much more accurate simulation of that kind of a dress. This is done with a finite element method. It's like with a triangle mesh. This is very challenging to do for technical reasons. What you can see on the right-hand side is the triangle mesh that's associated with the rendering on the right-hand side. And if you look closely, you'll notice that the triangle mesh is changing at almost every frame. And it's large. The triangles are large in the portions of the dress where there's less detail. It's flat, and it's smaller triangles in the regions where there's more detail, like wrinkles. Tracking where those are happening in the process of the simulation, and then remeshing the triangle mesh as that's occurring, and then calculating propagational forces in the triangle mesh rather than on the particle systems that I described. Those are all some of the technical challenges that are associated with this kind of physical simulation. Okay, so again, just scratching the surface today, but you'll be able to do a lot of really interesting things already in assignment 4, your last programming assignment. And historically, many of you will choose to do a dynamics-based project or a physical simulation project for your final project, final team projects as well. All right, folks, that's it for today. Good to see you all, and have a great spring break.